So now let's look at section 1.5, page 3. We're going to begin with a theorem. The theorem states that polynomials, rational functions, root functions, and trigonometric functions are continuous everywhere that's inside of their domains. So if they don't have a domain value, or if there is a non-domain value, then obviously they're not continuous there. So we'll start with a basic example. Determine where this given function is discontinuous. So that means basically we're looking for a value that is not in the domain. Where is this function not defined? Therefore, where is the domain? 0, and that will give us our discontinuity. So we're going to go ahead and take this denominator and we're going to set it equal to 0 and solve for x. There are actually two ways you can solve for x for this particular problem. You could use the square root property where you're going to isolate x so that you can take the square root of both sides. But whenever you take a square root, or really a root of an even power, you should be taking plus or minus the square root. So let's say you forgot that. Hopefully you would recognize that this was a second degree polynomial, the highest exponent. That meant you would have two answers. And so hopefully that would be your reminder for the plus or minus for where this function is discontinuous. Or perhaps you got that same answer a different way. Maybe you recognized that 9x squared was just a 3x that had been squared. 49 was just a 7 that had been squared. You have a subtraction of these two squared values, so you can have plus or minus the binomial of those squared values. Set equal to 0 would give you the negative and positive values for the same answer. Now, what if there was something we could do to the top of this? So let's go ahead and focus on that. It turns out if we can cancel a factor from the denominator with the numerator, then that is going to give you a whole or removable discontinuity at that point. But anything that's left after you cancel, if one of the denominators is still available, then when you find where that x value is not in the domain, that is going to give you infinite discontinuity, which is also referred to as a vertical asymptote. So let's look at example 3 to see that happen. I'm asked to find where this function is discontinuous and the types of discontinuity. So I'm going to factor the denominator and I'm going to factor the numerator. When I can cancel a numerator with a denominator, my function is still discontinuous at that x value, but specifically it's removable or whole discontinuity. Of the pieces that are left, when is the denominator 0? That is going to give me the infinite discontinuity values. For jump discontinuity, we would need to look at piecewise functions, but I think that's pretty straightforward. So the last thing to cover is a theorem, and basically it says, assume you have multiple functions which are continuous at some particular point A, and perhaps you have a constant C. Then the following will also be continuous at that same point A. You can basically add continuous functions to stay continuous. You can subtract, you can multiply, you can divide, but be careful that when you divide, it doesn't create a denominator with x, or in this case, a values that don't exist. And also, you can multiply by a constant or a scalar. So to see all of that, let's look at example 4. We're determining if this function is continuous from negative infinity to positive infinity. Taking the first term of 7 cosine of t, that's just really the cosine of t. We know that that's continuous on infinity, and all we've done is multiplied by a constant, so it's going to remain continuous. The cubed root of t is continuous, And so if we're just adding two continuous functions, we'll still have a continuous function. In math, when you use the phrase therefore, often you'll just use this symbol that's three dots that could be like in the corners of a triangle.